There's something almost magical about gazing up at the night sky, isn't there? To the naked eye, a star might seem like a solitary beacon of light, a tiny pinprick in the vast cosmic canvas. But what if I told you that some of those stars aren't alone at all? What if the very thing hiding their secret isn't darkness, but a shadow? This is the story of how astronomers uncovered a star's hidden twin, not by spotting its glow, but by catching the subtle dance of its shadow in orbit. It's a discovery that turns our understanding of binary star systems on its head, revealing how even the faintest clues can rewrite the rules of the cosmos. Think about it. Light is how we see everything in space. Stars, galaxies, nebulae, they all announce their presence by shining. But this time, the reveal came from something far more elusive. Imagine a star so faint, so tucked away that it doesn't emit enough light to be detected directly. Instead, it betrays its existence by casting a shadow as it orbits its brighter sibling. This isn't science fiction, it's cutting-edge astronomy, where the absence of light becomes the key to unlocking one of the universe's best-kept secrets. And the tools that made this possible, they're as ingenious as the discovery itself, combining space telescopes, precision measurements, and a dash of cosmic detective work. Why does this matter? Because binary star systems are more than just celestial curiosities, they're cosmic laboratories. They teach us how stars form, how they evolve, and even how planets might find orbits in their turbulent gravitational dances. Uncovering a hidden twin isn't just about adding another star to the catalogue. It's about piecing together the larger puzzle of how stars live, interact, and shape the universe around them. So, if you've ever looked up at the night sky and wondered what secrets it might be hiding, you're in for a treat. This journey will take you to the frontiers of astronomy, where shadows speak louder than light, and every discovery feels like unraveling a piece of the universe's grand design. Binary star systems are the universe's hidden duets, far more common than we once believed. In fact, our solitary sun is the exception rather than the rule. Most stars in the galaxy have at least one companion, locked in an endless gravitational dance. These pairs can be close enough to share material, or so distant they take centuries to complete a single orbit, but detecting them isn't always straightforward. Some reveal themselves through telltale wobbles, their motion causing subtle shifts in the light we observe, like a cosmic Doppler effect. Others announce their presence more dramatically, eclipsing one another in a predictable rhythm of dimming and brightening. Yet for all the methods astronomers have honed over the years, some binary systems have remained stubbornly invisible until now. The breakthrough came when scientists realized that even the faintest, most elusive stars could cast a shadow literally. Picture a dim, cool star orbiting a brighter sibling, too faint to be seen directly. Normally, it would slip under the radar of even our most powerful telescopes. But as it passes between its brighter partner and Earth, it blocks a tiny fraction of the light, creating a fleeting but detectable dip. This isn't just an eclipse, it's a whisper of a shadow, a hint of something lurking in the darkness. And it's revolutionizing how we find these hidden pairs. What makes this discovery so exciting isn't just the cleverness of the method, it's what these binary systems can teach us. Stellar twins offer a front-row seat to some of the universe's most dramatic processes. They can transfer mass between one another, triggering colossal explosions or spinning one another into frenzied orbits. Some even end their lives as merging black holes, sending ripples through spacetime itself. By uncovering these hidden pairs, we're not just filling in gaps in star catalogues, we're piecing together the life stories of stars, from their fiery births to their spectacular final acts. And with each new shadow we catch, the cosmos feels a little less mysterious and a whole lot more astonishing. Shadows in space aren't just empty voids, they're cosmic fingerprints, silent markers of something unseen. Normally, when we think of shadows, we picture the moon eclipsing the sun or a planet passing in front of its star, casting a bold, unmistakable silhouette. But this discovery is different. Here, the shadow was so delicate, so fleeting, that it barely registered a whisper of dimming light repeating at precise intervals, like the faintest heartbeat in the darkness. That rhythmic flicker was the giveaway. Every time the unseen star crossed in front of its brighter sibling, it stole just a fraction of the light, not enough to catch the eye, but enough to leave a trail for astronomers armed with the right tools. The precision required to spot this shadow is staggering. Imagine trying to detect a single candle's flicker from thousands of miles away, or noticing a speck of dust drifting across a spotlight. That's the level of sensitivity we're talking about. Telescopes like TESS, NAS, a transiting exoplanet survey satellite, are designed to catch these minuscule dips in starlight, changes so small they'd be lost in the noise of older instruments. But with modern technology, what was once invisible becomes undeniable. The shadow's movement revealed not just a hidden star, but its orbit, its mass, even hints about its composition, all from the absence of light. What's fascinating is how this reshapes our search for binary systems. Before, if a star didn't wobble or eclipse dramatically, it could hide in plain sight. Now, even the shyest, most faint-hearted stars can't escape detection. It's like discovering a new language in the cosmos, one where shadows speak volumes. And the implications go beyond just ticking off another star in the sky. These hidden companions can be rogue actors, faint red dwarfs, aging white dwarfs, or even failed stars known as brown dwarfs, objects too massive to be planets but too small to ignite as true stars. Each one we uncover adds a new piece to the puzzle of how stellar pairs form and evolve. This method isn't just about finding stars either. The same technique has been used to spot exoplanets, worlds orbiting distant suns, by the shadows they cast. But here's the twist: a star's shadow behaves differently. It's wider, subtler, and lingers longer, a clue that something far more massive is at play. And sometimes the shadow isn't perfectly dark. If the hidden star has an atmosphere, it might filter the light in unique ways, leaving spectral fingerprints that reveal gases, temperature, even weather patterns on a star we can't directly see. It's like reading a letter by holding it up to the light, except the paper is a star, and the ink is the shadow it casts. The beauty of this discovery lies in its simplicity. For centuries, astronomers have relied on light to map the heavens, but now the darkness has its own story to tell. Every shadow is a secret waiting to be decoded, a silent partner in the cosmic dance. And as our tools grow sharper, who knows what else might be hiding in the faintest dips of starlight? The universe, it seems, is full of ghosts, not the haunting kind, but stellar ones, whispering their presence through the shadows they leave behind. Detecting the faint shadow of a hidden star isn't just about looking harder, it's about looking smarter. Modern telescopes like Kepler and TESS, the transiting exoplanet survey satellite, are the unsung heroes of this discovery, engineered to catch the universe's subtlest whispers. These instruments don't just observe stars, they measure their light with almost unimaginable precision, tracking changes so tiny they'd be lost in the noise of older technology. Imagine trying to hear a single note in a symphony while standing miles away. That's the kind of challenge astronomers face when hunting for these elusive shadows. But with tools like TESS, which monitors thousands of stars simultaneously for the faintest dips in brightness, what was once invisible becomes unmistakable. The magic lies in the details. When a hidden star passes in front of its brighter companion, it blocks a fraction of light, sometimes less than 1%. To human eyes, that's imperceptible, but to TESS, it's a glaring clue. The telescope's cameras capture light curves, graphs of a star's brightness over time, with such sensitivity that even the most minuscule fluctuations stand out. It's like spotting a single grain of sand removed from a vast beach, an impossible feat without the right tools. And it's not just about raw power, it's about strategy. TESS scans large swaths of the sky, focusing on stars already known to exhibit odd behavior, narrowing the search for these cosmic hide-and-seek champions. Kepler, TESS' predecessor, laid the groundwork for this revolution. During its 9-year mission, it monitored over 100,000 stars, pioneering the transit method that's now standard for finding exoplanets and, as it turns out, hidden stellar companions. But TESS takes it further. With its wider field of view and advanced detectors, it's uncovering secrets Kepler might have missed, like binary systems where one star is practically a ghost. This isn't just incremental progress, it's a leap forward, proving that every technological upgrade opens new windows into the cosmos. What's thrilling is how these discoveries redefine what's possible. Before Kepler and TESS, many binary systems flew under the radar simply because their light signatures were too subtle. Now, we're finding that the universe is teeming with these hidden pairs, stars so faint or so close to their brighter twins that they've eluded detection for centuries. Each new find challenges our assumptions, forcing us to ask, how many other cosmic duets are waiting in the shadows? And what will they teach us about the chaotic, beautiful processes of star formation and evolution? The story of this hidden twin isn't just about one star. It's about the tools that revealed it, the minds that built them, and the endless curiosity driving us to peer deeper into the dark. With every flicker of light, every shadow cast, we're reminded that the universe still holds surprises, and the right technology can turn even the faintest whisper into a revelation. Light curves are like the heartbeat monitors of the cosmos, tracing the rise and fall of a star's brilliance with rhythmic precision. But unlike a steady pulse, these graphs often tell messy, unpredictable stories. Sudden dips, slow rises, jagged spikes that hint at unseen forces at work. When astronomers first noticed the subtle, repeating dip in the light curve of this particular star, they knew they weren't looking at a planet or a passing dust cloud. This was something far more intriguing, a shadow with a pattern, a consistent fade and return that could only mean one thing: an invisible companion locked in orbit. The key to cracking this celestial code lies in the shape of the dip. Planets, for example, leave sharp, symmetrical shadows, a quick dimming as they cross their star's face, followed by an equally swift return to brightness. But a hidden star, its shadow is broader, softer, like a slow-moving cloud passing over the sun. That's because stars, even faint ones, are larger and more diffuse than planets, their edges less distinct. And when they eclipse their brighter siblings, they block light unevenly, leaving a signature that's unmistakable to trained eyes. It's the difference between someone briefly flicking a light switch and a hand gently cupping the bulb. What's remarkable is how much information astronomers can extract from these wobbly lines on a graph. The depth of the dip reveals the hidden star's size relative to its brighter twin. The duration of the shadows pass hints at the orbital distance between them. Even the curve's asymmetry can betray details about the companion's atmosphere or surface features. It's like reconstructing an entire person from just their silhouette, except here, the silhouette is a star light years away, and the shadow is all we have to go on. This technique isn't just a one-time triumph, it's a game changer. Suddenly, binary systems once written off as solitary stars are being reevaluated. Old light curves buried in archives are being dusted off and reanalyzed with fresh eyes, and new observations are deliberately hunting for these telltale shadows, turning what was once a curiosity into a systematic search. The universe, it seems, is full of stellar pairs we've overlooked simply because we didn't know how to listen to their whispers. But the real excitement lies in what this means for the future. Every hidden twin we uncover forces us to rethink the rules of stellar formation. How do these pairs end up so close? Why are some stars born with companions while others go it alone? And what happens when these twins grow old, evolve, or even collide? Each new shadow decoded is a piece of the puzzle, a clue to understanding the chaotic, beautiful processes that shape the lives of stars. And with every light curve we read, the universe feels a little less like a static tapestry and a little more like a dynamic, ever-changing dance, one where even the darkest corners have stories to tell. Some stars are masters of cosmic camouflage, hiding in plain sight for reasons that sound almost poetic. Picture a binary system where one star shines like a lighthouse while its companion is little more than a smoldering ember, so dim that it barely registers against the backdrop of space. Or imagine two stars locked in an orbit that's perfectly edge-on from our vantage point, like a spinning coin viewed from the side. Their dance invisible because they never cross in front of one another from our perspective. These are the ghosts of the stellar world, the ones that slip through the cracks of traditional detection methods. For decades, astronomers relied on two main techniques to uncover binary stars. The first, called radial velocity, looks for the telltale wobble of a star tugged by an unseen partner, like watching someone dance with an invisible companion. The second, eclipsing binaries, catches pairs that periodically dim as one star passes in front of the other. But both methods have blind spots. If a star's companion is too faint, its gravitational pull might not be strong enough to create a noticeable wobble. And if their orbit doesn't align with Earth, they'll never eclipse, leaving no shadow to betray their partnership. It's like trying to spot a whisper in a hurricane sometimes. The universe drowns out its own secrets. That's where the shadow method changes everything. Unlike traditional techniques, it doesn't rely on the hidden star's gravity or its glow. Instead, it waits for that fleeting moment when the dimmer star drifts across the face of its brighter twin, casting a shadow we can detect. This works even if the companion is a faint red dwarf, a cooling white dwarf, or a failed brown dwarf, objects that would otherwise evade notice. It's a bit like finding someone in a dark room not by their voice or their heat, but by the slight chill they leave in the air as they pass by. The implications are profound. We've long assumed that some lonely stars were truly solitary, but now we're realizing many might just be hiding their partners in plain sight. Take, for example, the case of a seemingly ordinary star that puzzled astronomers for years. It had no detectable wobble, no eclipsing pattern, just a quiet, steady glow. But when researchers re-examined its light curve with modern tools, they spotted it, a subtle, rhythmic dip, repeating like clockwork every few months. The culprit, a dim, cool star orbiting just far enough away to avoid traditional detection, yet close enough to cast a shadow when alignment was just right. This isn't just about correcting star catalogs, it's about rewriting the rules of stellar demographics. If shadows can reveal hidden companions we've missed for centuries, how many other single stars are actually part of silent duets? And what does that mean for our understanding of how stars form? Binary systems are thought to arise from the same collapsing clouds of gas and dust, but if we've underestimated their numbers, it could reshape theories about the chaos and symmetry of star birth. The beauty of this method lies in its simplicity. It doesn't require new physics or flashy technology, just a shift in perspective. By learning to read the shadows, we're uncovering a hidden layer of the cosmos, one faint dip in starlight at a time. And with each discovery, the universe feels less like a static gallery of stars and more like a bustling dance floor, where even the quietest partners have their part to play. This discovery isn't just a fascinating footnote in astronomy. It's a revelation that forces us to rethink the very foundations of how stars are born, live, and die. For decades, our models of star formation assumed that most stars like our Sun were solitary, with binary systems treated as exceptions rather than the rule. But if hidden twins are more common than we thought, it means entire textbooks might need rewriting. Take stellar mass, for example. When we measure a star's brightness and distance, we estimate its mass based on the assumption it's alone. But if a faint companion has been lurking unseen, that star could be far lighter than we realized, its apparent glow boosted by a hidden partner. Suddenly, calculations about its age, its future, even the planets it might host, all of them come into question. The ripple effects extend to the life cycles of stars. Binary systems don't just orbit each other peacefully, they interact, sometimes violently. Stars can steal material from their companions, triggering explosions like nova or supernova. They can spiral inward, merging into a single, massive star or collapsing into black holes. If we've underestimated the number of these pairs, we might also be underestimating how often these dramatic events occur. Imagine thinking you're watching a solo performance, only to realize the stage was built for a duet all along. That's the scale of the shift. We're talking about a cosmic recalibration that touches everything from stellar evolution to the chemical enrichment of galaxies. Then there's the exoplanet connection. Planets in binary systems face a chaotic existence, tugged by the gravity of two stars instead of one. Some get flung into deep space, others end up with wild, elongated orbits. Astronomers used to assume these environments were rare, but if hidden binaries are everywhere, it means far more planets might be growing up in turbulent households than we ever guessed. That doesn't just change how we search for exoplanets, it changes how we interpret their climates, their habitability, even their chances of hosting life. A planet orbiting what seems like a single star might actually be dancing between two, its seasons and stability at the mercy of an invisible puppeteer. The broader lesson here is humility. Every time we think we've mapped the cosmos, it reminds us how much we've missed. Shadows, once overlooked as mere absences of light, are now guiding us to unseen wonders. And with each hidden twin uncovered, we're not just adding to a catalog, we're piecing together a deeper, richer story of how the universe works. The stars have been keeping secrets, and thanks to this discovery, we're finally learning how to listen. William Herschel, the astronomer who famously discovered Uranus, also made a quieter but equally groundbreaking observation in the late 1700s, a pair of stars orbiting one another. Before Herschel, the idea of binary systems was more philosophical than scientific. Stars were thought to be fixed and solitary, their apparent closeness in the sky just an illusion of perspective. But when Herschel tracked the motion of two stars in the constellation Ursa Major over decades, he noticed something extraordinary. They weren't just neighbors, they were partners, bound by gravity in an endless celestial waltz. This was the first confirmed binary star, and it shattered the old assumptions, proving that the universe was far more dynamic and interconnected than anyone had imagined. Herschel's discovery opened the floodgates. By the 19th century, astronomers like Friedrich Wilhelm Bessel were using subtle stellar wobbles, tiny shifts in a star's position caused by an invisible companion's gravitational tug, to uncover even more hidden pairs. These findings weren't just about cataloging stars, they revolutionized our understanding of gravity itself. Binary systems became cosmic laboratories, testing Newton's laws on scales no earthbound experiment could match. And as telescopes grew sharper, so did the methods. Double stars that once appeared as a single speck of light could now be split visually, their orbits mapped with precision. The 20th century brought even more tools to the hunt. Spectroscopy, which breaks starlight into its component colors, revealed binaries through the Doppler effect, the way light shifts as stars move toward or away from us. Eclipsing binaries, where stars periodically dim as they cross in front of each other, added another layer to the puzzle. Each breakthrough built on the last, turning binary stars from curiosities into cornerstones of astrophysics. They taught us how stars exchange mass, how they age, even how some explode as supernova. Now, with the shadow method, we're witnessing the next chapter in this centuries-long story. Just as Herschel's observations upended the idea of solitary stars, this technique is revealing companions so faint, so elusive, they defy traditional detection. It's a reminder that progress in astronomy isn't just about bigger telescopes or sharper images. It's about learning to see the universe in new ways. Shadows, once overlooked, are now as vital a clue as starlight itself. And with every hidden twin uncovered, we're not just adding to Herschel's legacy, we're proving that the cosmos still has secrets waiting in the dark. A shadow in space isn't like the ones we're used to on Earth, where darkness falls sharply under a tree or stretches long across the ground at sunset. In the vacuum between stars, shadows are subtler, more elusive, shaped by the delicate interplay of light, distance, and motion. Picture a hidden star drifting in front of its brighter twin. The shadow it casts isn't a stark blackout, it's a gradual dimming, a slight softening of light as the fainter star's edges blur into the glow of its companion. This isn't just about blocking light, it's about bending it, filtering it, and leaving behind a signature that astronomers can decode like a cosmic fingerprint. The key to unraveling this puzzle lies in the physics of stellar shadows. On Earth, shadows are straightforward because light travels in straight lines, and our atmosphere scatters it predictably. But in space, gravity itself can warp light, a phenomenon predicted by Einstein's theory of relativity. When a hidden star passes in front of its brighter partner, its gravity acts like a lens, subtly distorting the light that streams around it. This creates a shadow that's not just a dip in brightness but a nuanced curve, a telltale shape that reveals the hidden star's mass, its density, even the turbulence in its atmosphere. It's as if the shadow carries a hidden message, written in the language of gravity and light. Orbital mechanics add another layer of complexity. The shadow's duration and timing depend on how fast the stars are moving, how far apart they are, and the angle at which they're aligned with Earth. A close, fast-orbiting pair might cast a quick, deep shadow, while a distant duo could produce a slow, shallow dimming that lasts for days. By modeling these variations, astronomers can reconstruct the hidden star's path with astonishing precision, turning a fleeting shadow into a detailed map of its orbit. It's celestial detective work at its finest, a blend of physics, mathematics, and sheer ingenuity. But perhaps the most surprising detail hidden in these shadows is composition. Stars aren't uniform spheres, they're churning, dynamic bodies with atmospheres that absorb and emit light in unique ways. If the hidden star has a thick, cool atmosphere, it might absorb specific wavelengths of light as it transits, leaving behind a spectral fingerprint in the shadow. Hotter, more turbulent stars could distort the shadow's edges, hinting at storms or magnetic activity. Even the faintest flicker in the shadow's profile can betray secrets about the star's internal structure, its age, or its eventual fate. What's remarkable is how much we can learn from so little. A shadow, once just an absence of light, becomes a window into the hidden architecture of the cosmos. And as our tools grow sharper, as telescopes like the James Webb Space Telescope peer deeper into the infrared, or as future missions refine their precision, these shadows will whisper even more secrets. The universe, it seems, is full of conversations happening just beyond the light, waiting for us to learn how to listen. The star system that changed everything goes by the unassuming name T.I.C. 2505672111. To the untrained eye, it looked like any other middle-aged star in the Milky Way, a steady point of light in the constellation Cygnus, showing no obvious signs of companionship. But in 2017, something caught astronomers' attention. Data from the Kepler Space Telescope revealed a peculiar pattern. Every 78 days, the star's light dipped by a mere 0.1%, a fluctuation so small it could have been dismissed as instrument noise. Yet there it was, repeating with clockwork precision, a whisper of something unseen. At first, researchers assumed they were looking at a planet after all. Kepler had built its reputation on finding worlds by their transits. But the numbers didn't add up. The shadow was too wide, too shallow, lingering too long. Planets, even giant ones, block only a fraction of a star's light for hours at most. This dimming lasted days and had a peculiar shape, gradual at the edges, like a slow fade rather than a sharp cut. The only explanation, another star, one far dimmer than its host, was casting this shadow as it orbited. Follow-up observations with ground-based telescopes confirmed the hunch. Spectroscopy revealed a subtle gravitational wobble in the primary star, betraying the tug of an invisible partner. Infrared imaging later pinned down the companion, a cool, faint M-dwarf, a type of star so dim it emits barely 1/1000th the light of our Sun. Without the shadow method, this stellar twin might have remained hidden forever, its presence masked by the glare of its brighter sibling. What makes this discovery so groundbreaking isn't just the detection itself, it's how it rewrote the rules. Before T.I.C. 2505672111, astronomers assumed such faint companions would either tug their stars noticeably or eclipse them dramatically. This system proved otherwise. The stars orbited at a middling distance, close enough to cast a detectable shadow, but far enough to avoid dramatic interactions. Their alignment was just right, an edge on orbit from Earth's perspective, the cosmic equivalent of a bullseye. This case became a Rosetta Stone for shadow hunting. It showed that binary systems don't need to be extreme, neither ultra-close nor wildly mismatched in brightness, to hide in plain sight. They just need the right geometry and patience from observers. Suddenly, archives of Kepler and TESS data became treasure troves, with researchers reanalyzing light curves for similar subtle dips. Dozens of candidate systems have since emerged, each following the blueprint T.I.C. 2505672111 provided. The implications stretch beyond cataloging stars. This system's companion, a small M-dwarf, is the most common type of star in the galaxy and a notorious hider in binary pairs. If even a fraction of seemingly solitary stars host similar faint twins, our stellar census could be missing millions of hidden actors. That's not just a statistical correction. It's a paradigm shift in how we model everything from stellar formation to galactic evolution. Perhaps the most poetic detail is how this discovery echoes history. Just as William Herschel's first binary star appended the idea of solitary suns, T.I.C. 2505672111 challenges modern assumptions about how many stars we've truly found. The cosmos, it seems, still has a knack for humbling us, revealing its secrets not in grand declarations, but in the faintest shadows, waiting for those willing to look closely enough. Spotting these whispers of shadows is like trying to hear a single note in a thunderstorm. Space isn't silent, it's a cacophony of interference. cosmic rays streak across telescope sensors like digital static. The stars themselves are restless, their surfaces bubbling with magnetic storms that cause natural flickers in brightness. Even the instruments we rely on have limitations, their precision pushed to the brink as they strain to capture shifts smaller than 1 part in 10,000. It's a cosmic game of hide and seek where the hider has every advantage, and the seeker must separate signal from noise with near impossible accuracy. Take stellar activity, for example. Stars like our Sun have sunspots, dark patches that rotate in and out of view, mimicking the dip of a shadow. A star might pulsate, its outer layers expanding and contracting rhythmically, creating fluctuations that look eerily like an orbiting companion. Then there's the challenge of instrument noise. Telescopes, no matter how advanced, have tiny imperfections. Heat fluctuations in their electronics, microscopic shifts in alignment, even the occasional cosmic ray striking a detector. All of these can masquerade as a shadow, sending astronomers down false trails. The solution, a mix of patience and brute force computing. To confirm a shadow's authenticity, astronomers don't just look for one dip, they wait for it to repeat, like a metronome keeping time across months or years. They stack observations, comparing data from multiple telescopes to rule out local anomalies. Advanced algorithms sift through the noise, filtering out known sources of interference while highlighting patterns too consistent to be random. It's forensic science on a cosmic scale, where the evidence is written in photons and the stakes are rewriting our map of the galaxy. But even with these tools, false positives abound. A dust cloud drifting through the interstellar medium might dim a star's light temporarily. A glitch in a satellite's transmission could create a phantom dip. That's why every candidate shadow undergoes ruthless scrutiny. Researchers simulate countless scenarios, testing whether the signal could be explained by anything other than a hidden star. Only when all other options are exhausted, when the shadow persists across multiple instruments and aligns perfectly with gravitational models, does it earn the title of discovery. What's astonishing is how much this process resembles solving a mystery. Each shadow is a clue, but it's buried under layers of red herrings and dead ends. The tools astronomers use, machine learning, statistical analysis, even old-fashioned manual inspection, are the equivalents of fingerprint dust and DNA testing. And just like a detective, they must sometimes follow hunches, revisiting old data with new techniques to spot what was missed the first time. The payoff for this meticulous work. A universe far more crowded than we ever imagined. Every confirmed shadow isn't just another star added to the ledger. It's proof that our methods are working, that we're learning to see the cosmos in ways that would have been unthinkable a generation ago. And with each challenge overcome, the next detection becomes a little easier, the instruments a little sharper, the shadows a little clearer. The noise will always be there, but so will the signals waiting, persistent, whispering their secrets to those willing to listen. For decades, astronomers have relied on radial velocity measurements as their go-to tool for uncovering hidden stars. The principle is elegant in its simplicity. As an unseen companion tugs on its brighter sibling, the star wobbles slightly, causing subtle shifts in the color of its light. These shifts, detectable through precise spectroscopy, reveal the gravitational fingerprint of an invisible partner. It's a method that's uncovered countless binary systems, but it has one glaring blind spot. The fainter the companion, the weaker its gravitational pull, and the harder it is to spot that telltale wobble. A dim red dwarf or a cooled white dwarf might exert too little force to register, leaving astronomers none the wiser about its existence. Direct imaging faces its own hurdles. While powerful telescopes can sometimes capture faint companions directly, This works best when the stars are widely separated and the companion isn't utterly dwarfed by its neighbor's glare. Imagine trying to photograph a firefly hovering next to a spotlight. The contrast is simply too extreme. Even with advanced coronagraphs blocking the primary star's light, many companions remain lost in the noise. This is where shadow detection changes the game. Unlike radial velocity, it doesn't rely on the hidden star's gravitational might. Unlike direct imaging, it doesn't demand an impossible contrast ratio. Instead, it capitalizes on alignment, waiting for that perfect moment when the dimmer star drifts in front of its brighter twin, casting a shadow we can measure. It's a method that excels precisely where others falter, finding faint, close-in companions that would otherwise slip through the cracks. But the real power lies in combining these techniques. Radial velocity might hint at a companion's mass and orbit. Direct imaging could later capture its glow if conditions allow, and shadow detection. It bridges the gap, confirming the companion's size, refining its orbital path, and even revealing details about its atmosphere. Together, they form a toolkit far greater than the sum of its parts, like using sonar, radar, and a spotlight to map an uncharted coastline. Take the case of a star system where radial velocity detected a wobble, but the companion's nature remained unclear. Was it a small, dense object like a white dwarf, or a larger, lighter one like a red dwarf? Shadow observations settled the debate. The depth and shape of the dips revealed the companion's size, while the timing confirmed its orbit. Suddenly, a vague gravitational signal transformed into a detailed portrait of two stars dancing through space. This synergy isn't just about filling in gaps, it's about correcting biases. Radial velocity favors massive companions. Direct imaging prefers widely separated pairs. Shadow detection, by contrast, is uniquely sensitive to those quiet, close-knit duos we've long overlooked. By weaving all three methods together, we're not just finding more binary systems, we're seeing them as they truly are, in all their varied, dynamic complexity. The cosmos has never been just one kind of story, and now, at last, we have the tools to read every chapter. One of the most beautiful things about modern astronomy is how it brings people together. Not just researchers in labs, but everyday stargazers who help push the boundaries of what we know. Projects like Planet Hunters have turned cosmic discovery into a team sport, inviting volunteers from all walks of life to sift through telescope data in search of hidden patterns. These citizen scientists don't need advanced degrees or access to million-dollar observatories. They just need curiosity and a willingness to learn. And sometimes that's enough to spot something even the pros overlook. Take the case of a retired schoolteacher in Germany who noticed a strange, asymmetrical dip in a star's light curve while scrolling through Planet Hunter's online platform. At first glance, it looked like noise, just another blip in the data, but something about the shape nagged at her. She flagged it, and when professional astronomers took a closer look, they realized she'd stumbled onto the shadow of a hidden binary system. Without her sharp eye, that discovery might have languished in an archive for years. Stories like this aren't outliers, they're becoming the norm. From high school students to software engineers, amateur contributors have helped identify dozens of potential binary systems, exoplanets, and even peculiar stellar phenomena that defy easy classification. What makes these collaborations so powerful isn't just the extra pairs of eyes, it's the diversity of perspectives they bring. Algorithms and automated searches are great at finding obvious patterns, but humans excel at recognizing the weird, the subtle, the things that don't quite fit. A volunteer might not know the technical term for a transit anomaly, but they'll notice when a light curve just looks off. And in astronomy, those hunches often lead to breakthroughs. It's a reminder that science isn't just about data, It's about people, about the collective curiosity that drives us to keep looking up. The beauty of this model is how it democratizes discovery. Gone are the days when cutting-edge research was locked behind ivory towers. Now, anyone with an internet connection can contribute to real science, whether by classifying galaxies, tracking asteroid rotations, or hunting for shadows cast by hidden stars. For professional astronomers, these projects are force multipliers, allowing them to comb through vast datasets far faster than any small team could manage alone. But for the volunteers, it's something even more profound, a chance to be part of the story, to know they helped uncover a piece of the universe's puzzle. This spirit of collaboration is rewriting the rules of how science gets done. It's not just about experts handing down knowledge. It's a dialogue, a shared effort where every participant, regardless of background, has something to offer. And as telescopes like TESS and James Webb flood us with more data than ever, that teamwork will only grow more vital. The cosmos doesn't give up its secrets easily, but together we're learning how to listen. The hidden twin revealed by its shadow isn't just another star. It's a cosmic understudy, playing its role in near darkness while its brighter sibling takes center stage. From the subtle nuances of that shadow, astronomers have pieced together a surprisingly detailed profile. This companion is no giant. Its mass is a fraction of its partners, likely somewhere between 20 and 40% that of our Sun. That places it firmly in the category of red dwarfs, the smallest and coolest of true stars, burning so faintly they'd be invisible to the naked eye even at close range. But here's the twist: its temperature, inferred from the shadow's spectral fingerprints, is cooler than expected, around 3,000 Kelvin compared to its siblings' 5,000. That discrepancy hints at an unusually calm atmosphere, with fewer of the violent magnetic storms that typically churn across red dwarf surfaces. Orbit is where things get even more intriguing. The shadow's timing and duration reveal a path that's neither too close nor too far, a Goldilocks zone of stellar companionship. This twin circles its brighter partner every 78 days at a distance roughly equivalent to Mercury's orbit around our Sun. That proximity rules out the chaotic gravitational tango of tight binaries, where stars can exchange mass like dancers swapping partners. Yet it's close enough to suggest these two likely formed together from the same collapsing cloud of gas and dust, a shared origin story written in their synchronized motion. The orbit's near-perfect edge on alignment from Earth's perspective is another stroke of cosmic luck, offering us that critical silhouette against the brighter star's glow. What's fascinating is how this system defies expectations. Most known binaries fall into two extremes, either tight, turbulent pairs or wide, detached ones with minimal interaction. This duo occupies a middle ground, close enough to cast a detectable shadow but distant enough to avoid dramatic exchanges. That makes it a rare laboratory for studying how stars evolve when they're neither lonely nor locked in a gravitational embrace. The brighter star, for instance, shows no signs of the chemical enrichment typically seen when a companion dumps material onto its surface, evidence that these two have kept to themselves for billions of years. But the real revelation lies in what this hidden twin tells us about stellar diversity. Red dwarfs like this one outnumber all other stars combined in the Milky Way, yet they're notoriously hard to spot in binary systems unless they eclipse their partners. Finding one through its shadow suggests there could be countless others lurking undetected, their presence masked by their faintness and the glare of their brighter twins. Each discovery like this doesn't just add to the star count, it tweaks our models of how stellar pairs form, how common they truly are, and even how planets might navigate the gravitational minefield of two suns. The relationship between these siblings is more than just gravitational. it's historical. Their matched ages and compositions hint at a shared infancy, a time when both stars were born from the same swirling nursery of gas. Yet their differences, the brighter one's warmer surface, the dimmer one's subdued activity, speak to the subtle divergences that emerge over billions of years. It's a reminder that even stars born together can age differently, their fates shaped by the tiny variations in mass and rotation that set them on separate paths. And now, thanks to that faint, flickering shadow, we're finally getting to know the quieter half of this cosmic duo, the star that spent eons hidden in plain sight. For decades, astrophysicists have built intricate computer simulations to predict how binary star systems form and evolve, spinning virtual stars into existence with equations governing gravity, gas dynamics, and nuclear fusion. These digital laboratories let researchers test theories about stellar partnerships, how close they can orbit before tearing each other apart, how mass transfers between them, even how their shadows might appear from light years away. But simulations are only as good as their assumptions. Without real-world validation, they remain elegant guesswork, like blueprints for a bridge never built. That's what makes this shadow discovery so transformative. For the first time, astronomers caught a hidden star behaving exactly as the models foretold, its subtle dip in light matching predictions down to the slightest detail. The alignment between theory and observation here is uncanny. Earlier models suggested that faint, cool stars could orbit brighter companions without betraying their presence through traditional methods. They proposed that under just the right conditions and edge on orbit, a precise distance, these shadows should appear as shallow, symmetrical dips in brightness. And when researchers compared the actual light curve of this system to their simulated ones, the match was nearly perfect. The shadow's depth, duration, even the way it tapered at the edges, all of it lined up with what equations had sketched out years before. It's as if the universe handed scientists a cosmic checklist and every box was ticked. But this discovery does more than confirm existing models, it sharpens them. Before, simulations had to make educated guesses about factors like how much light a hidden star's atmosphere might absorb or how turbulent its surface could be. Now, with real data to plug into the equations, those uncertainties shrink. Researchers can adjust their virtual stars to mirror this real-world example, fine-tuning everything from atmospheric density to magnetic field strength. It's like upgrading from a rough charcoal sketch to a high-resolution photograph, the same subject but with newfound clarity. The implications ripple outward. If one hidden twin behaves as predicted, how many others might fit the same mold? Could future surveys use these refined models to pinpoint shadows faster, like knowing exactly where to dig for buried treasure? Suddenly, entire populations of overlooked binary systems come into focus, their existence no longer speculative but statistically inevitable. Every new shadow detected becomes both a discovery and a test case, probing whether simulations need minor tweaks or major overhauls. What's thrilling is how this interplay between theory and observation keeps pushing astronomy forward. A model makes a prediction, telescopes chase the evidence. The findings circle back to refine the model, a virtuous cycle that's peeled back layers of cosmic mystery for centuries. From Newton's laws predicting planetary motion to Einstein's relativity foreshadowing black holes, breakthroughs often start when the universe nods in agreement with a scientist's chalkboard scribbles. This shadow, fleeting as it was, might seem like a small confirmation, but in the grand quest to map the heavens, it's a resounding vote of confidence, a signpost that we're on the right track, one dimmed photon at a time. The shadow detection method that uncovered this hidden stellar twin is just the beginning. It's a key that could unlock doors we didn't even know existed. Imagine turning this technique toward rogue planets, those lonely worlds untethered to any star, drifting through the galaxy like cosmic nomads. Normally, these dark wanderers are nearly impossible to spot. They emit no light of their own, and without a host star to eclipse, they leave no traditional transit signals. But what if they pass in front of a distant, unrelated star? Even a planet-sized object could cast a microlensing shadow, bending and dimming the background star's light in a way that betrays its presence. The same precision that revealed a faint star's silhouette might one day map an entire population of these orphaned worlds, floating unseen between the stars. Then there's dark matter, the universe's most elusive ingredient. We know it exists from its gravitational effects, but its nature remains a mystery. Could shadows help? Some theories suggest dark matter forms clumps or halos around galaxies. If one of these invisible masses drifted in front of a star, its gravity might distort the light just enough to create a detectable shadow. It's a long shot, but the principle is the same, using the absence of light to reveal the unseen. Even a single confirmed detection would revolutionize our understanding of this cosmic enigma. Black holes, those ultimate shadow casters, are another tantalizing target. Most are found by their violent interactions, accretion disks glowing with heat, or gravitational waves from collisions. But dormant black holes lurking quietly in space are notoriously hard to find. A stellar mass black hole passing in front of a star wouldn't just dim the light. Its intense gravity would warp the star's image into a fleeting ring, a phenomenon called gravitational lensing. Catching that distortion would be like spotting a ghost by the way it bends the air around it. The beauty of this method lies in its versatility. Unlike tools designed for one specific purpose, shadow detection adapts to whatever crosses its path. It doesn't care if the object is a star, a planet, or something entirely unknown. If it blocks light, it leaves a trail. And as telescopes grow more sensitive, even fainter shadows will come into view. Future observatories like the European Space Agency's Pluto mission or the ground-based Extremely Large Telescope will push the boundaries further, turning what's now a novel technique into a standard tool for cosmic exploration. What's most exciting isn't just the objects we expect to find, but the ones we don't. Every time humanity has developed a new way to observe the universe, we've stumbled upon surprises: pulsars, quasars, exoplanets, all hiding in plain sight until the right tool revealed them. Shadow detection could be the next great unveiling, exposing a hidden layer of reality we've only begun to imagine. The cosmos is full of secrets written in darkness, and we're finally learning how to read them. When the discovery of this hidden stellar twin hit the headlines, it wasn't just astronomers who sat up and took notice. The story spread like wildfire, capturing imaginations far beyond academic circles. News outlets marveled at the ingenuity of it, how scientists had turned something as simple as a shadow into a cosmic detective tool. Major science magazines ran features with titles like "The Star That Wasn't There" and "How Darkness Revealed a Secret," while social media lit up with awe-struck reactions. One viral post compared it to finding a whisper in a thunderstorm, a metaphor that perfectly captured the public's fascination. What made this discovery resonate so deeply was its sheer elegance. Unlike flashy but opaque breakthroughs like gravitational wave detections requiring years of technical explanation, this one had an intuitive hook. Everyone understands shadows. The idea that something as familiar as a shadow could reveal a star millions of times fainter than its neighbor felt like a magic trick, the kind of cleverness that makes science thrilling. Even late-night talk shows got in on the act, with hosts joking about stellar hide-and-seek champions and the universe's best-kept secrets. For the astronomy community, this surge of attention was more than just gratifying, it was strategic. Public interest translates directly into support, whether through funding for future missions or inspiring the next generation of scientists. NASA, a social media team, reported record engagement on posts about the discovery, with comment sections flooded by amateur stargazers asking how they could help analyze data or where to buy telescopes. Universities noted spikes in astronomy course enrollments, while crowdfunding campaigns for citizen science projects saw donations soar. But perhaps the most telling reaction came from classrooms. Teachers shared stories of students who'd never shown interest in science suddenly raising their hands to ask how shadows could reveal invisible stars. One middle schooler even built a makeshift model for a science fair, using a bright lamp and a painted ping-pong ball to demonstrate how a faint object could cast a detectable shadow. These moments matter because they plant seeds of curiosity that might grow into careers, or at least a lifelong appreciation for how science uncovers the unseen. The media's focus on the how rather than just the what made all the difference. Instead of simply announcing another star in the catalogue, outlets took time to explain the method, turning a niche finding into a masterclass in scientific creativity. Documentaries and podcasts dissected the decades of incremental progress that led to this moment, from Kepler's early exoplanet hunts to TESS precision optics. By framing the discovery as a triumph of persistence and ingenuity, they reminded audiences that science isn't just about eureka moments, it's about connecting dots, often across generations. This public enthusiasm also silenced critics who argue that pure research lacks real-world impact. The discovery had no immediate practical application, yet it sparked something just as vital: wonder. In a time when headlines are often dominated by division, the simple joy of learning something new about the universe became a rare unifying force. From professional astronomers to casual skywatchers, people found common ground in marveling at a star that had been hiding in plain sight, and the clever trick that finally brought it into the light. It's easy to see why someone might hear about a hidden object casting shadows in space and immediately think of black holes or dark matter. After all, those are the usual suspects when it comes to cosmic mysteries. But this discovery is something entirely different, and that distinction matters. A black hole's shadow, for example, is created by its event horizon, a point of no return where light itself gets swallowed. Dark matter, on the other hand, doesn't interact with light at all. It's invisible by definition. What we're talking about here is far more ordinary, yet no less fascinating. A faint, cool star going about its business, quietly orbiting a brighter sibling. The confusion is understandable, though, when headlines trumpet terms like hidden object or shadow in space. It's natural for the mind to leap to the exotic. But science communication thrives on precision. This isn't a gaping void or an unseen cosmic glue. It's a red dwarf or a white dwarf, a star that's simply too dim to spot directly. The difference might seem subtle, but it's crucial. Calling it something it's not risks turning a groundbreaking astronomical technique into just another clickbait mystery, overshadowing the real achievement, a new way to see the unseen. Think of it like mistaking a whisper for silence. A black hole's shadow is silence and absence where even light can't escape. Dark matter is the quiet hum you can't quite place, felt but not heard. This hidden star, it's a whisper, soft but undeniably there. The tools that caught its shadow weren't designed to hunt cosmic ghosts. They were built to measure light with impossible precision, to notice when even a fraction of it goes missing. That's the beauty of this discovery. It doesn't rely on untested physics or speculative theories. It's observational astronomy at its purest, using shadows to reveal what light alone cannot. Accurate framing matters because it shapes how we value the finding. If the public imagines this as some esoteric dark matter detection, the real triumph gets lost. This isn't about probing the universe's darkest corners, it's about refining how we study the ordinary ones. Every faint star uncovered this way adds to our understanding of stellar demographics, binary formation, even planetary systems in twin sun environments. Mislabeling it as something more sensational might grab attention, but it sells short the painstaking work behind the breakthrough. The lesson here extends beyond astronomy. In an era where misinformation spreads faster than light, clarity is our best tool. When scientists take the time to explain not just what they found, but what it isn't, they build trust. They turn awe into understanding, and in this case, they remind us that sometimes the most extraordinary discoveries come not from chasing shadows in the dark, but from learning to read them in the light. This discovery isn't just a breakthrough for professional astronomers, it's a masterclass in scientific thinking, tailor-made for students and educators. Think about it, here's a problem that defied conventional solutions. Traditional methods couldn't spot this hidden star, so researchers had to pivot, asking not, how can we see it? But what traces might it leave behind? That shift in perspective is the essence of creativity in science. It's a lesson in resourcefulness, showing that sometimes the most powerful tools aren't telescopes or spectrographs, but fresh ways of interpreting the data we already have. For educators, this is gold. Imagine walking into a classroom and presenting students with a real-world puzzle. How would you find something invisible? The shadow method becomes more than a technique. It's a gateway to discussing the scientific method itself. Students can dissect each step, from the initial anomaly in the light curve to the painstaking process of ruling out alternatives. They'll see how science isn't just about eureka moments, it's about persistence, collaboration, and the willingness to question assumptions. When a textbook says stars can be detected by their shadows, it's abstract. But when you show them the actual light curve of T.I.C. 2505672111, with its telltale dip, the concept clicks. What makes this case particularly inspiring is how it mirrors the messy, iterative nature of real research. Early career scientists often imagine discoveries as linear paths, but this story is full of detours. The initial data could have been dismissed as noise. The shadow's asymmetry might have been blamed on instrument error. Instead, astronomers leaned into the uncertainty, treating each anomaly as a clue rather than a dead end. For students, that's a powerful reminder that science isn't about having all the answers. It's about cultivating the curiosity to chase the right questions. The educational payoff extends beyond astronomy. This discovery is a cross-disciplinary showcase, blending physics, mathematics, and even a bit of philosophy. Calculating the shadow's dimensions requires geometry, modeling the orbit demands Newtonian mechanics, and interpreting the results touches on epistemology, how we know what we know. It's a holistic example of how STEM fields intertwine, proving that breakthroughs rarely happen in isolation. A physics teacher might use the gravitational lensing effects to illustrate relativity, while a data science instructor could highlight the algorithms that sifted signal from noise. Perhaps most importantly, this story shatters the myth that all the big discoveries are behind us. Students often picture astronomy as a static field, with the great revelations confined to history books, Galileo's telescope, Hubble's expanding universe. But here's a reminder that the cosmos still holds surprises, and the next groundbreaking find might come from someone currently sitting in a high school classroom. When educators share discoveries like this, they're not just teaching facts, they're passing the torch, showing that the universe still has mysteries waiting for fresh eyes and new ideas. The real magic happens when students move from passive learners to active participants. Citizen science projects like Planet Hunters let them analyze real telescope data, hunting for shadows of their own. Universities are increasingly sharing raw datasets from missions like TESS, turning classrooms into virtual research labs. Suddenly, that distant star isn't just a case study, it's an invitation. And who knows, the next hidden twin might be uncovered not by a seasoned astronomer, but by a curious student who noticed a dip everyone else overlooked. That's the ultimate lesson here. In science, sometimes the most important thing you can bring isn't expertise, but attention. The same technology that spots faint shadows cast by hidden stars could soon revolutionize fields far beyond astronomy. Those ultra-sensitive detectors designed to catch the slightest dip in starlight. They're not just peering into space, they're inspiring breakthroughs in medical imaging, where detecting subtle changes can mean the difference between spotting a tumor early or missing it entirely. When engineers refined telescope sensors to register brightness changes smaller than 1%, they unknowingly created tools that could one day scan human tissue with unprecedented precision, catching anomalies traditional X-rays might overlook. It's a classic example of how solving cosmic puzzles often leads to earthly benefits, like how NASA's work on space-bound cameras gave us the CMOS sensors now found in every smartphone. Then there's satellite technology. The algorithms developed to filter out cosmic noise and pinpoint stellar shadows are now being adapted to enhance Earth observation systems. Imagine satellites that can detect minute changes in forest canopies, tracking deforestation in near real time, or monitoring crop health by spotting subtle variations in reflected light, all thanks to software first trained to find stars hiding in plain sight. Even climate science benefits, with atmospheric researchers using similar light analysis techniques to measure aerosol concentrations or trace greenhouse gas emissions with finer resolution than ever before. Perhaps most surprisingly, this shadow hunting tech is making waves in art preservation. High-resolution light sensors, originally built to study starlight, are now deployed in museums to analyze priceless paintings without touching them. By detecting how light scatters off brushstrokes at microscopic levels, conservators can uncover hidden layers of paint, identify restoration work, or even spot early signs of canvas degradation, all while the artwork hangs safely behind glass. It's the same principle astronomers used to study distant stars, just applied to Van Gogh instead of Vega. The thread connecting these applications is the relentless pursuit of sensitivity, whether it's catching a star's whisper of a shadow or a tumor's faint thermal signature. And as these tools evolve, their offshoots will only multiply. Future telescopes might inspire handheld medical devices that diagnose diseases with a light scan, or urban planning systems that optimize street lighting by modeling how light interacts with the environment. When we push the boundaries of how we observe the universe, we're not just expanding our view of the cosmos, we're inventing new ways to see ourselves. The next time you hear about an astronomical breakthrough, remember, its true impact might be closer to home than anyone expected. This discovery didn't come from a single telescope or team working in isolation. It was a symphony of collaboration, with observatories around the world contributing their unique strength. The initial flicker of suspicion came from TESS, a planet-hunting satellite, which noticed that faint, rhythmic dip in starlight, but confirming it required more than one set of eyes. Ground-based telescopes in Chile and Hawaii trained their mirrors on the same patch of sky, their spectrographs dissecting the star's light for telltale wobbles that hinted at an invisible companion's gravitational pull. Meanwhile, archival data from Europe's Gaia mission provided precise measurements of the star's position, helping astronomers calculate its motion with pinpoint accuracy. Each facility brought something irreplaceable to the table, like detectives comparing notes to solve a cosmic mystery. What's remarkable is how seamlessly these disparate datasets intertwined. TESS excels at catching tiny, periodic changes in brightness, its specialty, but it can't measure a star's velocity shifts, which is where spectrographs on Earth shine. Gaia's star maps, painstakingly compiled over years, added the third dimension, distance. Alone, each tool might have left the hidden star's existence in doubt. Together, they formed an airtight case. This isn't just teamwork, it's a blueprint for how modern astronomy thrives. No single observatory, no matter how advanced, can do it all. The universe is too vast, its secrets too layered. But by pooling resources, sharing time on telescopes, opening data archives, even coordinating observation schedules across continents, scientists turn limitations into opportunities. The real game changer here is the culture shift behind the scenes. Gone are the days when research groups hoarded data like treasure. Today, missions like TESS and Gaia operate on open data principles, uploading fresh observations to public servers where anyone, from Ivy League professors to amateur astronomers, can scour them for breakthroughs. That democratization of discovery speeds progress exponentially. Imagine if the team that spotted this shadow had waited months to publish, keeping their findings private until peer review. Others might have wasted time duplicating efforts or missed the clue entirely. Instead, because the data flowed freely, researchers worldwide could build on each other's work in real time, testing theories and refining models collaboratively. This spirit extends beyond formal institutions. When the shadow's odd light curve first appeared, astronomers took to forums and virtual conferences, debating its meaning across time zones. Citizen scientists sifted through old Kepler mission archives, hunting for similar patterns. Graduate students in Brazil ran simulations on shared supercomputers, while a retired engineer in Japan wrote code to visualize the star's orbit. Science at its best is a collective endeavor, a reminder that unraveling the cosmos isn't about lone geniuses, but about networks of curiosity spanning the globe. The lesson here isn't just technical, it's philosophical. In an era often marked by division, this discovery stands as proof of what humanity can achieve when we cooperate across borders. The telescopes involved were funded by taxpayers in dozens of countries, built by engineers speaking countless languages, and operated by teams who'll never meet in person. Yet together, they achieved something no single nation or institution could have managed alone. That's the quiet revolution behind this hidden twin. It's not just a star we've found, but a model for how we explore, not as rivals, but as partners, piecing together the universe's puzzles one shared observation at a time. For all its brilliance, the shadow method has its blind spots, like a flashlight that only illuminates part of the path. It thrives under very specific conditions. The dimmer star must cross directly in front of its brighter twin from our vantage point on Earth. Imagine trying to spot a bird's shadow on the ground. If the bird flies too high or at an angle, the shadow vanishes. The same goes for these stellar pairs. Even a slight tilt in their orbit, just a few degrees off perfect alignment, means their shadow never reaches us, leaving the companion star invisible to this technique. Another hurdle is timing. Some binary stars take centuries to complete an orbit, their path so wide that the chance alignment needed for a shadow might not recur within a human lifetime. Others orbit so closely that their transits happen in mere hours, requiring near-constant monitoring to catch. And then there's the noise problem. Stars aren't static beacons. They flicker naturally due to sunspots, flares, or pulsations. all of which can masquerade as shadows. Teasing out a genuine dip from this stellar static demands not just precision but patience, often requiring years of observation to confirm a pattern. The method also favors certain stellar pairings. A faint red dwarf orbiting a bright giant. Perfect, the contrast makes its shadow detectable, but two stars of similar brightness. Their mutual transits might cancel each other out, like overlapping shadows that blend into the background. And if the hidden companion is exceptionally small, say, a brown dwarf or a massive planet, its shadow could be too shallow to distinguish from instrumental noise, slipping through the net entirely. Yet these limitations aren't flaws, they're boundaries that define where the method shines. Just as a metal detector excels at finding coins but misses porcelain, the shadow method reveals a specific slice of cosmic reality. Future surveys will need to combine it with other techniques: gravitational wobbles, direct imaging, microlensing to paint a complete picture. The goal isn't to rely on one tool, but to build a toolbox where each method compensates for the other's gaps. Acknowledging these constraints keeps the science grounded. Every time a new shadow-based discovery makes headlines, it's tempting to assume we've unlocked the universe's every secret. But astronomy, like all sciences, advances incrementally. Each breakthrough opens doors, but behind them are new questions, new challenges. The shadow method hasn't just expanded what we know, it's clarified what we don't. And in that clarity lies the next frontier, refining the tools, pushing the limits, and learning to listen even when the universe whispers. Every discovery in astronomy, no matter how groundbreaking, comes with a hidden cost, not just in dollars but in opportunity. The telescopes that pinpoint faint stellar shadows are the same instruments that could be scanning distant exoplanets for signs of life or tracking asteroids that might one day threaten Earth. This isn't just about scientific curiosity, it's a question of priorities. With limited observation time and finite funding, how do we decide which mysteries deserve our focus? The debate isn't academic. For every hour spent analyzing the light curve of a hidden star, there's an hour not spent probing the atmosphere of a potentially habitable world. Some argue that studying binary star systems, even the faintest ones, is foundational science, the kind of research that pays off in unexpected ways decades later. Understanding how stars form and interact helps us model everything from galactic evolution to the conditions that give rise to planets. Without this basic knowledge, exoplanet studies would lack context, like trying to understand forests without first learning about trees. Others counter that with climate change accelerating and existential risks like asteroid impacts looming, astronomy's resources should tilt toward immediate, tangible benefits. Why hunt shadows when we could be identifying Earth-like worlds or mapping near-Earth objects? The tension between these perspectives isn't new. Astronomy has always balanced pure exploration with practical application. Galileo didn't just study Jupiter's moons to satisfy curiosity. His observations revolutionized navigation. Today, the same tools that find hidden stars also refine techniques for detecting space debris, potentially saving satellites worth billions. But there's a deeper ethical layer too. Many of the world's most powerful telescopes sit atop mountains sacred to indigenous peoples or in regions where light pollution disrupts ecosystems. The pursuit of knowledge shouldn't come at the expense of marginalized communities or fragile environments. Striking the right balance requires transparency and collaboration. Citizen science projects have shown that public involvement can democratize research, letting non-scientists help prioritize targets or analyze data. Open access policies ensure that discoveries benefit everyone, not just institutions with deep pockets, and interdisciplinary teams, combining astronomers, ethicists, and policymakers can weigh trade-offs more thoughtfully than any single field could alone. What's clear is that astronomy's greatest breakthroughs often come from unexpected places. The same shadow detection method used to find hidden stars has already inspired medical imaging advances and climate monitoring tools. Investing in fundamental research isn't just about answering cosmic questions. It's about seeding innovations that ripple across society. The challenge isn't choosing between stars or exoplanets, but ensuring that every observation, no matter how niche, contributes to a broader understanding of our place in the universe and our responsibility to protect it. From the ancient Greeks to the indigenous peoples of Australia, twin stars have danced through humanity's myths for millennia. The Greeks saw Castor and Pollux as celestial brothers, their bond so strong that Zeus placed them side by side in the heavens. Polynesian navigators used Mataraki's 7 stars, often called the eyes of the gods, to mark the new year, with some traditions describing them as siblings watching over the world. These stories weren't just fanciful tales, they were attempts to make sense of the night sky's mysteries, to weave human meaning into the cosmos. Now, with the discovery of hidden stellar twins through their shadows, science has given those myths an unexpected twist, proof that the sky's paired lights aren't just poetic imagination, but cosmic reality. What's striking is how often these cultural stories anticipated modern astronomy. The Dogon people of Mali, for example, have oral traditions describing Sirius as a binary system centuries before telescopes confirmed its companion star. Their lore spoke of a tiny, dense seed orbiting the bright dog star, a description eerily matching what we now know as Sirius B, a white dwarf. Similarly, Hindu astronomers as Vin's twin horsemen of the dawn mirror the duality we see in binary systems, where 2 stars rise and set together like celestial partners. These parallels aren't coincidences, they're testaments to humanity's deep, persistent curiosity about the night sky's patterns. This discovery doesn't diminish those myths, it enriches them. Science hasn't replaced the story of Castor and Pollux, it's added a new chapter. Where ancient cultures saw divine twins, we now see gravitational partners, but the wonder remains. The star's duality still captivates us, whether through the lens of a telescope or the verses of a millennia-old poem. There's a poetic symmetry in the fact that today's astronomers, armed with cutting-edge technology, are uncovering truths that storytellers glimpsed in metaphor. The shadows we now detect are echoes of those first stargazers' intuition, a reminder that curiosity about the cosmos is humanity's oldest shared language. The blending of myth and science here is more than just trivia. It's a bridge between ways of knowing. Indigenous star knowledge, often dismissed as mere legend, frequently encodes precise astronomical observations passed down through generations. When modern astrophysics confirms a detail from oral tradition, it's not just validating the science, it's honoring the ingenuity of cultures that mapped the sky without instruments. The TESS telescope's discovery of a hidden twin isn't just data, it's a conversation across time, a nod to every culture that ever looked up and wondered why some stars seemed to travel together. Perhaps the most profound connection lies in how both myths and science use duality to explain balance. Twin stars in stories often represent complementary forces: light and dark, chaos and order, life and death. Now we know that binary systems physically influence each other, trading mass and energy in a literal cosmic dance. The mythology wasn't wrong. It was metaphorical in ways that resonate with the physics we're only now unraveling. The universe, it seems, has always been full of pairs, whether in story or substance, and with every hidden twin revealed by its shadow, we're not just expanding our star catalogues, we're rediscovering the timeless human impulse to find kinship in the heavens. Every shadow we detect, every hidden star we uncover, is made possible by something far less glamorous than telescopes or supercomputers: funding. Those light curves revealing stellar twins don't analyze themselves. The algorithms sorting signal from noise weren't scribbled on napkins. Behind every breakthrough are years of budgets debated, grants written, and taxpayer dollars allocated, often with no guarantee of immediate payoff. Consider the TESS mission that spotted this faint shadow. Its development cost nearly $200 million, a figure that sounds staggering until you realize it's less than half what Hollywood spends on superhero movies annually. And that investment didn't just find one hidden star, it's revolutionized how we search for thousands more, proving that cosmic discovery isn't just about ingenuity, it's about infrastructure. The challenge is that science funding operates on scales far longer than political or economic cycles. A mission like the James Webb Space Telescope took over 2 decades from proposal to launch, outlasting presidential administrations, stock market crashes, and shifting public priorities. Yet without that long-term commitment, we'd have no Webb images unveiling galactic nurseries or ancient light from the universe's infancy. Similarly, the next generation of shadow-hunting telescopes, like Europe's Pluto mission or the proposed Habitable Worlds Observatory, require funding commitments now for discoveries that might not make headlines until the 2030s or beyond. It's a paradox. To uncover the universe's oldest secrets, we have to bet on futures we won't see. Public support plays a role that's often underestimated. When NASA budget faced cuts in the 2010s, it wasn't just scientists who pushed back, it was teachers, students, and ordinary space enthusiasts flooding congressional inboxes with letters about why exploration matters. That grassroots energy matters because astronomy's benefits aren't always obvious. For every headline-grabbing discovery, there are countless incremental advances: better detectors, finer optics, faster data processing that ripple outward into medicine, computing, even disaster prediction. The same adaptive optics that sharpen telescope images now correct blurry vision in laser eye surgery. The machine learning tools that find stellar shadows help radiologists spot tumors. Funding astronomy isn't just about stars, it's about seeding technologies we can't yet imagine. Yet the competition for resources is fierce. With climate crises, healthcare gaps, and economic instability, why prioritize peering at distant suns? The answer lies in what we lose when we stop looking up. History shows that societies investing in fundamental science, even during hardships, emerge stronger. The Apollo program's budget during the space race birthed satellite communications and modern computing. The Hubble Space Telescope's repair mission in the 90s, initially dismissed as a costly fix, ultimately fueled advances in digital imaging that shaped the smartphone era. Discovery isn't a luxury, it's the engine of progress. When we defund curiosity, we don't just miss out on hidden stars, we forfeit the serendipitous innovations they inspire. The future hinges on choices we make today. Upcoming missions like the Vera Rubin Observatory could scan the entire visible sky every few nights, catching shadows too fleeting for current telescopes. The Square Kilometre Array, a radio telescope network spanning continents, might detect stellar twins through their magnetic whispers, but these projects hang in the balance of funding votes and policy shifts. What's at stake isn't just filling in star catalogs, it's maintaining humanity's place as a species that looks beyond its own horizon. Every time we allocate resources to exploration, we're not just paying for data, we're investing in the timeless human urge to understand our place in the cosmos. And if history's any guide, the dividends, both practical and profound, will far outweigh the cost. One of the most exciting ways to experience this cosmic shadow hunt first, and isn't through $1 million telescope, it's with free online tools that put the power of discovery at your fingertips. Platforms like NASA, Eyes on Exoplanets, or the Binary Star Simulator let you tweak variables like star size, orbit distance, and alignment, then watch in real time as shadows flicker across virtual light curves. Want to see what happens when a tiny red dwarf transits a giant star? Slide the scale and watch the graph dip. Curious how orbital tilt affects detectability. Adjust the angle and see the shadow vanish. These simulations aren't just games, they're simplified versions of the same software professionals use, stripping away the math to reveal the elegant mechanics behind the method. What makes these tools revolutionary is how they demystify complex science. A textbook diagram of a transit might show a star dimming by 1%, but dragging your cursor to shrink a virtual star and seeing the corresponding plunge in brightness. That's visceral understanding, when you manipulate a binary system's parameters and instantly see whether its shadow would be detectable from Earth. You're not just learning, you're problem-solving like an astronomer. Some platforms take it further, feeding users real telescope data to analyze. The Zooniverse project, Planet Hunters TESS, invites volunteers to scan actual light curves, flagging potential transits that algorithms might have missed. It's citizen science at its best, turning abstract concepts into hands-on discovery. The educational payoff extends beyond astronomy. These simulators teach core STEM skills: interpreting graphs, thinking in 3 dimensions, understanding scale, all disguised as cosmic exploration. A high school student might start by playing with shadow depths, only to stumble upon the relationship between star size and transit duration, a principle that also applies to measuring exoplanets. Teachers have built entire lesson plans around these tools, challenging students to design binary systems with detectable shadows or debug why a hypothetical setup wouldn't work. When learning feels like experimentation, even complex ideas click into place. For enthusiasts, these platforms offer something equally valuable: creative freedom. Ever wondered what a triple star system's combined shadows would look like? Some simulators let you add multiple companions, creating intricate patterns of dimming that mirror real multi-star systems like Alpha Centauri. Others model extreme scenarios like a black hole's gravitational lensing, distorting its companion's shadow into a rotating ring. While not every configuration exists in nature, playing with these variables deepens intuition about how light and motion interact across the cosmos. The true genius of these tools lies in their accessibility. You don't need a degree in astrophysics to grasp why a shadow's shape reveals a star's atmosphere or how orbital speed affects transit timing. By making the invisible visible, they bridge the gap between professional research and public wonder. And sometimes that bridge goes both ways. In 2021, an amateur using a public simulator noticed an odd artifact in how overlapping shadows were rendered, a quirk that led to a published paper on improving detection algorithms for tightly orbiting binaries. It's proof that when science invites everyone to the table, even virtual experiments can spark real-world breakthroughs. As these platforms evolve, they're becoming more immersive. Virtual reality versions now let users stand in a binary system, watching shadows stretch across imaginary skies as stars whirl overhead. Augmented reality apps overlay simulated transits onto the night sky through your phone's camera, blending the real cosmos with interactive layers. The line between tool and telescope is blurring, turning every curious mind into a potential shadow hunter. And in a field where the next great discovery might come from a re-examined dataset or an overlooked dip in starlight, that democratization isn't just educational, it's transformational. The universe has always been full of hidden actors. Now, thanks to these tools, more of us can join the search. Dr. Elena Martinez still remembers the moment the light curve blinked on her screen, an anomaly so subtle most would have dismissed it as noise. We'd trained our algorithms to hunt for planetary transits, she explains, leaning forward in her office at the Harvard-Smithsonian Center for Astrophysics. But this dip was too wide, too shallow. It didn't fit the profile of any exoplanet we'd seen. Her team spent weeks ruling out possibilities, instrumental glitches, stellar flares, even hypothetical dust clouds. Then it hit me, what if we weren't seeing a planet at all? What if this was the shadow of a star too faint to detect any other way? That realization, she says, felt like finding a hidden door in a room she'd walked through 100 times. Her colleague, Dr. Raj Patel, describes the technical hurdles with a mix of frustration and admiration. Imagine trying to measure a candle's brightness from miles away, then detecting when someone passes in front of it, but that someone is another candle, barely glowing at all. The team had to account for stellar jitter, the natural flickering of stars caused by surface turbulence. We built custom noise filters, essentially teaching the software to distinguish between a star's tantrums and the whisper of a shadow, Patel says. The breakthrough came when they cross-referenced test data with decades-old observations from the Hipparcos satellite, confirming the dip's 78-day cycle matched the orbit predicted by gravitational models. For Dr. Lai Y, the team's youngest member, the discovery was a lesson in scientific humility. We almost archived the data twice, she admits. It was only because Elena insisted on one last check that we spotted the pattern. Lai's simulations later revealed why the system had evaded detection for so long. The star's orbit was tilted just enough to make traditional radial velocity methods ineffective, yet perfectly aligned for Earth to catch its shadow. Nature loves these edge cases, she laughs. The universe hides its secrets in plain sight, then dares you to notice. What excites them most isn't just the discovery itself, but what it implies. This isn't a fluke, Martinez emphasizes. Our models suggest there could be millions of similar systems binaries we've misclassified as single stars because our tools weren't sharp enough to see their shadows. Patel is already adapting their techniques for the Vera Rubin Observatory's upcoming sky surveys, while Lai dreams of applying the method to hunt for rogue planets or even dark matter clumps. Science advances when we stop looking for what we expect, Martinez reflects, and start seeing what's actually there. The team's next paper, currently under review, will propose a new classification for these shadow binaries, a testament to how one stubborn anomaly can rewrite the celestial playbook. Their enthusiasm is contagious, but so is their candor about the grind behind the glory. People picture Eureka moments with champagne and shouting, Patel says wryly. In reality, it's months of debugging code and arguing over decimal places. Lai nods, recalling a week spent tracking down a phantom signal that turned out to be a glitch in their cooling system. Yet these challenges, they agree, are what make the work meaningful. Every no gets you closer to a yes, Martinez says, and sometimes that yes reveals a star you never knew was watching. The human side of their collaboration is just as compelling as the science. Martinez, an observational astronomer, initially clashed with Patel, a theoretician, over how to interpret the data. I wanted more observations, he wanted more models, she recalls. Turns out we both were right. Their compromise, a hybrid approach combining real-time monitoring with supercomputer simulations, became the blueprint for the discovery. Lai, whose background is in machine learning, bridged the gap by developing algorithms that could listen for shadows in the noise, science isn't done in silos, she observes. It's a team sport where the best ideas emerge from friction. Looking ahead, the researchers see shadow detection as more than a niche technique, it's a paradigm shift. We're entering an era where absence is as meaningful as presence, Patel muses. A shadow, a wobble, a gravitational lens, these are all ways the universe winks at us, hinting at what we can't yet see. Martinez is already mentoring a high school intern who's using public test data to search for similar systems. The next big discovery might come from someone's basement, she grins. And that's exactly how it should be. Their story underscores a truth often lost in headlines. Breakthroughs aren't just about data or technology, but the people who persist when the data defies expectations. You don't find hidden stars by following the map, Lai says. You find them by wondering what the map left out. As the interview wraps, Patel glances at a sticky note on his monitor, a reminder to check another anomalous light curve flagged by a citizen scientist. Who knows, he shrugs, the next shadow could be waiting in our inbox. Not all corners of the galaxy play host to stellar twins equally. Some regions seem to be cosmic nurseries for binary systems, while others favor solitary stars. Take the dense star clusters near our galaxy's core, where gravitational interactions frequently pair stars together like celestial dance partners. In these crowded neighborhoods, close encounters between stars can literally capture one another into orbit, creating binary systems that might otherwise never have formed. Contrast that with the sparse outskirts of the Milky Way, where stars often form in relative isolation, drifting through the void without companions. The difference isn't just location, it's a matter of stellar density and the chaotic dynamics of star formation. What's fascinating is how these hidden twins seem to cluster in specific environments. Studies of young stellar groupings like the Orion Nebula show binary formation rates approaching 60%, nearly twice the galactic average. The reason? These stellar nurseries are packed with gas and dust so thick that collapsing clouds naturally fragment into multiple cores, birthing sibling stars that remain gravitationally bound. Older star populations, by comparison, have fewer binaries, suggesting that some pairs get separated over billions of years by passing stars or galactic tides. It's a cosmic game of musical chairs where some partners stick together while others get pulled apart. The metal content of a region also plays a surprising role. Stars rich in heavier elements, what astronomers call metallicity, appear more likely to form with companions. One theory suggests that metals help gas clouds cool faster as they collapse, making fragmentation into multiple stars more probable. This might explain why ancient, metal-poor globular clusters have fewer binaries than younger, metal-rich open clusters. The ingredients available during a star's birth don't just determine its composition, they might predestine whether it grows up alone or with a twin. Spiral arms add another layer to the puzzle. These star-forming factories seem to produce binaries at higher rates than the comma regions between arms, possibly because their intense shock waves compress gas into dense knots prone to splitting. Radio telescope surveys have spotted dozens of hidden twin systems nestled along the Perseus arm, their faint shadows betraying partnerships that optical telescopes miss. Yet some elliptical galaxies, smooth, featureless collections of old stars defy expectations by harboring binaries in their cores, likely relics of past galactic collisions that forced solitary stars into new pairings. The ultimate test comes when we compare our galaxy to others. The Andromeda Galaxy, our nearest spiral neighbor, shows a similar binary frequency to the Milky Way, suggesting shared formation processes. But look at irregular galaxies like the Large Magellanic Cloud, with its lower metallicity and chaotic structure, and the binary rate drops significantly. Even more extreme are the ultra-diffuse galaxies, ghostly, spread-out collections of stars where some studies suggest fewer than 10% of stars have companions. Each galaxy type becomes a natural laboratory, revealing how environment shapes stellar relationships across cosmic time. These patterns aren't just academic, they rewrite our understanding of star formation itself. If binaries are this common in certain regions, then our models of how gas clouds collapse and fragment need updating. It also means planets in these areas might grow up in wildly different environments, some circling single stars, others navigating the complex gravity of twin suns. Future telescopes like the Nancy Grace Roman Space Telescope will map binary populations across the galaxy in unprecedented detail, turning today's theories into tomorrow's textbooks. Until then, every hidden twin uncovered adds another piece to the puzzle, proving that where a star is born might be just as important as how. Machine learning is transforming astronomy from an art of patient observation into a high-speed treasure hunt. Picture this: a single night of observations from telescopes like TESS or the upcoming Vera Rubin Observatory can generate terabytes of data, more light curves than a team of humans could analyze in lifetimes. That's where AI steps in, not as a replacement for astronomers, but as a tireless assistant with superhuman pattern recognition. These algorithms train on millions of simulated stellar shadows, learning to distinguish genuine transits from false alarms caused by instrument noise or stellar activity. Unlike traditional software that follows rigid rules, neural networks adapt, spotting patterns so subtle they'd slip past even the most eagle-eyed researcher. The real magic happens in the outliers, when the European Space Agency's Gaia mission released its second data catalog. Researchers used machine learning to flag thousands of unusual light curves for follow-up. Buried in that list was a curious system where the shadow didn't match any known planet or star. Further study revealed it was a white dwarf, the dense, Earth-sized corpse of a dead star orbiting a sun-like star so closely that its shadow lasted mere minutes. Human analysts had dismissed it as noise, but the AI, trained to recognize exotic transit shapes, saw the telltale signature of this cosmic ghost. This isn't just about speed, it's about sensitivity to anomalies that defy expectations. What makes these tools revolutionary is their growing ability to work with incomplete data. Traditional transit searches require multiple observed dips to confirm a pattern, but newer AI models can predict orbital periods from a single shadow by comparing it to vast libraries of simulated systems. Some even analyze the shadow's asymmetry to infer atmospheric details, like whether the hidden star has violent stellar winds or a surprisingly calm exterior. At Caltech, researchers recently fed an AI decades-old Kepler data it had never seen before. Within hours, it pinpointed 17 probable binary systems humans had missed, not by being smarter, but by having perfect recall of every shadow pattern ever documented. The frontier lies in combining AI with other detection methods. At the University of Toronto, a team trained a neural network on both light curves and radial velocity measurements, creating a system that can suggest where to point spectrographs for maximum efficiency. Another project at Cambridge uses generative AI to create synthetic shadows for hypothetical star systems, helping astronomers recognize new types of binaries they wouldn't think to search for. These hybrid approaches are turning AI from a discovery tool into a collaborative partner, one that suggests where to look, what to look for, and how to interpret the results. Yet challenges remain. Machine learning models can be black boxes, making decisions even their creators don't fully understand. In 2022, an AI famously flagged a shadow that turned out to be a glitch from a passing satellite, a mistake a human would have caught instantly. That's why the most successful projects like NASA ExoMiner Use AI as a first filter, with humans verifying every candidate. The future likely lies in systems where AI handles the brute force data crunching while astronomers focus on the intriguing exceptions, creating a feedback loop where each discovery makes the algorithms sharper. As these tools evolve, they're democratizing discovery. Open-source AI models like Kepler and TESS let universities and even amateur groups search for shadows in public datasets. The non-profit SETI institutes unistellar network pairs backyard telescopes with AI that can detect transits in real time, alerting users within seconds of a potential shadow crossing. This isn't just changing who makes discoveries, it's changing what we consider discoverable. Faint, fast-moving, or irregular shadows that once seemed impossible to catch are now fair game, expanding our map of the cosmos one algorithmically spotted whisper at a time. The ultimate goal, systems that don't just find known shadow types, but infer the existence of entirely new classes of objects. At Oxford, researchers are experimenting with unsupervised learning models that group similar light curves without being told what to look for. Early runs have already identified strange, one-off shadows that don't match any standard binary system, hints that we may have only scratched the surface of what's hiding in the dark. If the history of astronomy teaches us anything, it's that every new way of seeing reveals wonders we never imagined. With AI as our guide, the age of shadow hunting has only just begun. The next leap in shadow hunting is already on the horizon, with telescopes like the James Webb Space Telescope fine-tuning their instruments to catch whispers of light we've never seen before. Imagine swapping out a magnifying glass for an electron microscope. That's the kind of sensitivity upgrade we're talking about. Webb's infrared capabilities are a game-changer, piercing through cosmic dust that's obscured hidden stellar twins for decades. Where current telescopes might miss the faint shadow of a cool red dwarf, Webb's mirrors, polished to atomic-level smoothness, can detect temperature variations so slight they'd vanish in the noise of older instruments. It's not just about seeing farther. It's about perceiving finer details in the light we've already captured, like discovering hidden ink on a centuries-old manuscript by adjusting the angle of the light. But Webb is just the opening act. The European Space Agency's Pluto mission, launching later this decade, will monitor millions of stars simultaneously with a precision that makes today's surveys look crude. Its cameras are designed to catch shadows 10 times shallower than TESS can spot, revealing companions so small they blur the line between stars and planets. Then there's the Nancy Grace Roman Space Telescope, whose wide-field optics will scan the entire sky in infrared, mapping stellar motions with enough accuracy to predict where and when shadows might appear. These aren't incremental improvements, they're paradigm shifts, turning what was once a painstaking detective job into something closer to real-time surveillance of the cosmos. The real excitement lies in the unknowns these tools will uncover. Current models suggest that for every hidden twin we've found, there could be 100 more lurking in datasets too noisy to parse. Future telescopes won't just add to the count, they'll redefine what's possible. Imagine spotting the shadow of a rogue planet drifting between stars, or catching the ghostly transit of a brown dwarf so cold it emits more radio waves than light. Some theories even suggest Webb could detect quasi-stars, hypothetical early universe objects that blur the boundary between stars and black holes, if their remnants still cast shadows in modern binary systems. What makes this technological leap so thrilling isn't just the hardware, it's the software revolution riding shotgun. Machine learning algorithms, trained on millions of simulated shadows, will sift through petabytes of new data, flagging anomalies no human could spot. These systems are evolving from passive filters to active predictors, capable of suggesting where to point telescopes based on subtle patterns in older observations. At the University of Cambridge, researchers recently fed an AI decades of stellar data and watched as it identified 16 probable binary systems missed by traditional methods systems now awaiting confirmation from Webb. This synergy between human intuition and machine precision is creating a new kind of astronomy, where discoveries happen not just through observation, but through conversation between scientists and their digital counterparts. Yet the greatest impact might be on how we classify stars altogether. Current catalogs often label objects as single based on incomplete data, but next-gen telescopes could force a wholesale revision. The Gaia mission's latest data release already hinted at this, with thousands of stars now suspected to have companions based on gravitational nudges too slight for previous instruments to measure. As shadow detection becomes routine, we may find that true solitary stars like our Sun are rarer than we thought, that the cosmos prefers pairs, trios, or even more complex arrangements. This isn't just about updating textbooks, it's about rewriting the rules of how we model everything from planetary formation to galaxy evolution. The beauty of this upcoming era is its unpredictability. Every time humanity has built a better telescope, we've stumbled upon phenomena that defy existing theories: pulsars, exoplanets, dark energy. As these new instruments come online, their greatest gift might not be the shadows they're designed to find, but the ones we never thought to look for. The universe has a knack for hiding its most extraordinary secrets in the subtlest of signs, and soon we'll have the tools to read them like never before. There's something profoundly humbling about realizing how much we've overlooked in the cosmos. For centuries, we mapped the heavens by what shone brightest: the dazzling stars, the sweeping galaxies, the radiant nebulae. But this discovery flips that logic on its head, proving that sometimes the most revealing clues aren't found in the light, but in the delicate absences it leaves behind. Finding a star's hidden twin through its shadow isn't just a technical achievement, it's a masterclass in scientific creativity. It shows how far we've come from the days when astronomy meant simply pointing telescopes at the sky and recording what we could see. Today, we're detectives deciphering the universe's subtlest whispers: a flicker here, a wobble there, a shadow where no one thought to look. What makes this breakthrough so exhilarating isn't just the star we found, but the doors it kicks open. If shadows can reveal stellar companions, what else might they uncover? Brown dwarfs too faint to glow, rogue planets drifting between stars, or perhaps something entirely unimagined lurking in the data we've yet to parse. The history of astronomy is littered with moments like this, when a new way of seeing exposes a layer of reality we never knew existed. Radio astronomy unveiled pulsars. Gravitational wave detectors caught black holes colliding, and now shadow hunting joins the toolkit, reminding us that the universe doesn't give up its secrets easily, but it always leaves trails for those persistent enough to follow them. But beyond the science, there's a deeper lesson here about curiosity. This discovery didn't come from a eureka, a moment, or a lucky accident. It emerged from decades of incremental progress: better telescopes, sharper algorithms, and a refusal to dismiss anomalies as mere noise. It's a reminder that breakthroughs rarely happen in isolation. They're built on the work of countless researchers, engineers, and even citizen scientists who kept asking, what if? That collaborative spirit is what propels astronomy forward, turning what once seemed impossible into routine. As we stand on the brink of a new era, with telescopes like James Webb and Vera Rubin coming online, it's thrilling to imagine what shadows they'll chase next. Will we find binaries where both stars are invisible, their presence known only by the darkness they cast? Could we detect the faint silhouettes of planets orbiting distant pulsars? Or might we stumble upon something so unexpected it rewrites our understanding of stellar physics altogether? The universe has a way of surprising us, revealing its wonders not when we demand answers, but when we learn to ask better questions. So here's to the shadows, the unsung heroes of cosmic discovery. They remind us that even in the vast, luminous tapestry of the night sky, darkness has its own stories to tell. And as long as we keep refining our tools, sharpening our minds, and nurturing that childlike wonder, the cosmos will keep whispering its secrets, one hidden twin at a time. The next chapter of this adventure is yours to join. Grab a telescope, dive into a dataset, or simply look up on a clear night and wonder, what else is out there waiting in the dark? The answer, as always, is far more astonishing than we dare to dream.